SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. So, we just concluded our discussion on the genetic models and their use or utilization in formulation of exploration criteria for taking the example of the volcanogenic massive sulphide deposits and such kind of genetic models in many other important genetic types such as the lode type gold deposits or the sediment hosted massive sulphide deposits, Olympic the IOCG type deposits, all these genetic models whatever state they are in terms of their formulation can be translated into formulation of exploration criteria when we understand the processes, the critical processes which operate in a much larger scale than coming down to the district scale and deposit scale processes which actually are vital in giving rise to the deposit in its form that we see in its enriched form. Today we will be briefly discussing about a method, this geochemical method of prospecting. We will just have a brief idea about the method and see how much we could discuss about it, how much we can learn about this method and getting into the fundamental principles, because most of the some amount of discussion which we had before as regards to the geochemical prospecting or exploration, they have the present state of their the present state in which we use them. They have come of age because of availability of very high precision analytical equipment by which we have been able to analyze to very low concentrations in the parts per billion or parts per trillion, and we target to generate geochemical anomaly maps on local as well as regional scale. And in this exercise actually what we intend to generate is the geochemical anomaly map, and we will see how it could be in different scales. But before we actually go on to pick up a sample from anywhere on the earth's crust in our search for an ore deposit, we need to have the basic background information about the deposit characteristics in terms of some preliminary idea, its disposition in the crustal rocks, and its at least in the way it occurs sometimes under cover. To some geological information which is obtained during the reconnaissance and the detailed survey stages, some idea has to be there with us. So, here, so this is as we discussed before, that its application of geochemistry to explore for or delineation of hidden ore bodies which are lying under cover, and it requires fundamental understanding of the behavior of elements in the primary and secondary geochemical cycles. The primary geochemical cycles are the first stage formation of the ore bodies by the process of either a magmatic fractionation or a hydrothermal deposit. But once the deposit is formed, the metals that are enriched in the deposit will always tend to migrate under concentration gradient to different media, like within the rock itself, within the rock matrix, or within the covered soil. Soil pore spaces are filled up with water and they enhance the mobility of these metals, and they get dispersed in the soil horizon which are above, in the plants, in the water bodies, and so on. And we divided them into different geochemical exploration, the geochemical prospecting types such as lithogeochemical, pedogeochemical or soil geochemical, hydrogeochemical and biogeochemical. So, today's discussion will be mostly focusing on the soil geochemical exploration, because it needs some fundamental understanding about soil, because soil is the media from which we will be sampling. And so, here the fractionation of elements during the successive differentiation from solar nebula we discussed before, and that was the preliminary stage, first stage of dispersion and element fractionation, and during the melting or crystallization of rocks, this goes in the primary process. And the secondary, the mobility during solid state recrystallization, mobility in a fluid medium, which is the main focus as far as the exploration is concerned, because mobility during solid state crystallization can always take place during the metamorphism of an existing ore body, or there are some ideas that are coming up that even the already formed sulphide ore body could possibly undergo some amount of melting, but the process how efficient it is to redistribute or enhance or further enrichment of the ore bodies in terms of rich ore is not very well constant as of now. And the mechanical dispersion that takes place by the mechanical disintegration of the ore bodies, and the absorption desorption via vis-a-vis surficial processes including microbial transportation. Even though we do not have much of scope into the details of the microbial process, but the adsorption desorption process play a vital role in the secondary mobility of the metals. Any geochemical prospecting program, it requires a detailed planning, the requisites and orientation. For basically what we understand by this orientation, we will discuss in a little bit of details. The materials that we are trying to analyze: rock, soil, water, air or vegetation. The methods, the analytical techniques, appropriate method, detection limits, accuracy and reproducibility, interpretation, and that is what is the trick of the trade. There could be textbook knowledge will always, or any standard information about the geochemical prospecting will always be referring to these parameters such as accuracy and reproducibility or precision and accuracy. These are the two terms which are very widely referred to in any literature dealing with analysis of geological materials. Accuracy, we understand that whether we use a method, the results that is coming up from that particular equipment by whatever analytical protocol that we are establishing, whether this analysis should be accurate or not. So, this accuracy can only be checked by many cross or analyzing in many different instruments, many different methods, and many of the analytical protocols are very well established, like X-ray fluorescence spectrometry or atomic absorption spectrophotometry or inductively coupled plasma mass spectrometer. So, these are the equipment where by use of reference standards and this kind of analysis are produced to fair degree of accuracy, and it goes without saying that without checking of the accuracy, any data that is being generated is not usable and for any meaningful interpretation for a geochemical prospecting program. And reproducibility is the thing, is a factor by which the machines, the analytical procedures, analytical protocol stability, and the range by which a particular and the result is reproducible when replicate measurements are taken by that machine, and that is one of the important parameters that we report. For example, we report a certain metal in the form of ppm. Say in a rock we analyze for copper, and we report that copper is present in 50 ppm, and we have to give the figure as to plus minus what, plus minus, I would say plus minus 0.5 ppm possibly would make it a very good analysis, or I can also put in terms of 5 percentage, 5% or 2% or 1%. This is all determined by regular routine analytical protocols, and the interpretation of the chemical data when they are translated into the form of geochemical anomaly is actually the trick of the trade. Whenever we talk about a geochemical prospecting program, geochemical by using analytical technique and what remains there is the most fundamental aspect is the sampling. This is one of the most important aspect of the geochemical prospecting program, because it is not only that the sampling has to be representative, any biasness in the collection of samples will lead to erroneous result, and in addition to that there must be some amount of sampling strategy which also should be adopted to see to it that what we have sampled is actually will be telling us giving us the right information. I will just discuss them a little bit while now. Whenever we talk about a soil, that we are taking a sample of soil which is an overburden in several feet or sometimes several tens of meters in thickness, which are the product of the rock weathering and they form the overburden. So, these soils generally can be of two types. One is a residual overburden, what is called residual overburden. So, residual overburden essentially means that the soil has formed in situ, means wherever we are finding the soil is actually the product of degradation of the rocks which is just lying beneath the soil profile, soil horizon, and in that case the soil will inherit the characteristics of the rock from which it is derived, although the details of the soil forming process is beyond the scope of the discussion here, but at least we must understand what the soil type is in a particular area or the soil profile, and the other type of the soil that we might see in any particular area could be transported overburden, and this actually is a tricky affair. Whenever we are analyzing soil sample from an area for interpretation in terms of a geochemical anomaly to detect hidden ore body, it definitely depends on whether we have sampled the residual overburden or the transported overburden. Transported overburden essentially means that the soil which is observed on any particular area lying over the rock is actually not the product of the degradation of the rock which is lying below, but they are transported from the soil formed in some place and they have been transported by the action of gravity or by some transporting agent and deposited on the area where we are seeing them. So, in principle the transported overburden will not be reflecting any of the characteristics of the terrain where in terms of the hidden ore body, but then it is not a very easy job to distinguish between the overburden residual whether transported. We can just have a brief idea from this. So, this shows a generalized soil profile, and as we all know that the soil profile is going to be different from different geographical domains, and for example, the first column over here is the soil profile which develops in a temperate humid climate. This is the Portsel, and it has the soil horizons A0, A1, A2, B, C and D. Normally the D refers to the bedrock, which is the, and this of course corresponds to the residual soil as per our classification scheme, and the immediately layer which lies above is the C zone, which is the zone of weathering of the bedrock or till, and they are loose and partly decayed, and they do preserve the texture of the rock to some extent. The parent material for the overlying A and B, they are the parent material, because if this D is essentially unweathered or undegraded material, then it is essentially the B and the A horizons are essentially derived from the C horizon, where it mimics the rock structure. Sometimes there some of the resistant oxides they possibly stay back in this particular region, and then the B layer is the brownish color due to eluviation, this accumulation of iron and manganese oxide and organic matter and clays, and they are blocky or prismatic in structure, a high capacity for trace elements. Most of the trace elements get are enriched in this zone. The zone of eluviation in semi-arid regions forming calis or this calcium carbonate, you could just give a comparison. So, here the situation is such that the A0 zone is actually is mostly humus rich and partly decomposed organic debris, and it only reflects it does not reflect much about what is the subsurface condition is. And this A1 also, it is a dark colored organic rich material mixed with mineral matter, and then this A2 layer, which is light colored zone of maximum elevation, where that means maximum leaching has been taken place in this zone, and this content they rich in clays, colloidal oxides, and then the organic matter percolating rainwater. These are well developed in port zones in the humid dry climate, and so the soil profile which is shown in a temperate kind of a climate will be different from the soil profile which is occurring in a semi arid region, in which we will not have a B layer, and in place of that we will have a calcium carbonate rich caliche. This is an arid desert region where we will not be having any of this A0, A1 or A2 zones, and this is a juvenile formation of just below a mountain, the foothill region, where these zones will be developed, but their thickness will be different, they will be less, even though these are not to scale. In a normal temperate climate, we could expect this kind of a zonation of the soil profile and also the thickness by which they will be present. So, the importance of the soil profile is that whenever we are planning a geochemical exploration program, geochemical prospecting program, we must be very sure exactly what we should be sampling. So, normally the A0 or the A1 type of zones, depending on, they will be varying from place to place from different geographical domain. So, samples have to be necessarily be taken from the A2 or the B horizons if we want to analyze, or if we say that this soil characteristics should be actually reflecting on the subsurface hidden ore body of any particular enrichment of any particular metal. These are some of the some ideas can be obtained from looking at these figures, which are pretty old, but then still very informative regarding what exactly happens and how do we distinguish between transported and residual overburden. So, this particular figure, where one is shown on a plan view and the one on a section. So, this black body is representing the hidden ore body and is on a sloping surface, and these dotted curves are the contour lines, and it shows a normal weathering process by which the ore body is getting weathered, and it is forming a fan shaped dispersion pattern below the foothill, and in which case the element of interest will be present only in a very larger area, but in a much more in a diffuse manner without giving any sharp anomaly in anywhere in the area. And so, these are the different types of hydromorphic patterns one can expect. This is a situation in which there is an ore body, the section is shown here, and this is a situation which will be happening if there is an ore body and the metals have migrated or have diffused through in the concentration gradient and will be dispersed in this, and if we take the soil sample from here, we are likely to get some signal from there. And here it shows the hydromorphic pattern in the with respect to the water table, and the cross section is more informative here, and this dotted line here is the water table, and since and this is the surface, and water table has water table, the water groundwater generally flows in a hydrostatic gradient as has been shown by the arrow, and this particular groundwater will corrode or will dissolve the ore body, that is constituents of the ore body, and will disperse in the down the gradient in the soils which are over here. And in these cases, all these cases which is shown in a plan view here, we will be always be getting the concentration of this particular element of interest in a far more diffuse manner than what could be possibly a very sharp sharp value that we expect sometimes, that if if there is an ore body somewhere here, and these are all the soil, and if we measure the concentration of any metal, then if we are going to take the samples from different points and if we plot, then it is going to give us some sharp anomaly for any particular metal that we are interested in. So, this is an example in which it would give us some clue as to identify whether that particular area the soil could be a transported soil or could be a residual soil. This is an epigenetic pattern over in transported overburden. Similarly, the plan view over here, these are the soil which is there in the on a slope, and the groundwater is flowing, and the actual anomaly will be distributed all over these areas and following the flow of the groundwater, and sometimes the pattern may also be similar in residual overburden. So, there are certain situations in which the identification of the residual and the transported may not be that very sharp, and these are some interesting pattern in terms of the dispersion. These are the dispersion pattern in surface drainage. If we have an ore body here and it has to be a radial kind of a drainage pattern, then the metal of interest will be getting dispersed in the stream water only, but only in the stream water, but no sediments. Here in the stream water and sediments with peniplanation depending on the slope and the topography of the area, and here the stream sediments only by erosion of soil anomaly, and in this case it is a swamp sediment, in this case it is lake water sediments, and these are the principal type of dispersion pattern in subsurface drainage which we might expect and can plan the sampling program for a geochemical survey. And this is also an interesting situation where this is a river, and here is the hidden ore body, the buried ore body, and this is the slope of the water table in this direction, and this water table will always follow and will get exposed on the stream, which is will be something like where the river is flowing. So, the water table will always follow a pattern like this, and whatever any ore body which will be lying here somewhere as shown in this diagram will always carry the metals in solution and will get discharged on the river bed, and that is how we could always get a concentration. For example, if we are if this happens to be the water body in the area, then and that this happens to be the regional slope, then the concentration of the elements the metal of interest will always be higher in the downstream direction compared to the region somewhere region here. So, this gives some of the ideas at how this metal of interest or the element of interest can get dispersed. This is the section view of that that is what is shown here. This is the floodplain, this is the barren underflow, and this is the ore body which is getting dispersed by the hydromorphic forming a hydromorphic fan pattern. What basically what is being shown here are essentially they are called as the trails and fans. In most of the cases these can be termed as the trails, or some of the cases where you have seen in the forming the alluvial region getting mechanically degraded from the parent ore body, they form some pattern which can be called as fans, like like the situations which we were showing here, when this kind of a situation can be called as forming as the dispersion pattern, which can be called as fan, just making a shape which is can be very well familiarly termed as a fan, and as compared to situations which could be just the trails. It's many of these situations, many countries, many geographical regions, including what we have in the Indian subcontinent. We have the formation of these soils for very long geological time, and these soils, they do form something which is generally called as the regolith, and its regolith is essentially can be called as paleo soil. And depending on the time during which they have formed, they show some well defined patterns. The way exactly we saw a soil profile, we could also have this kind of regolith profile, and in many of the countries like in Australia, and these regoliths are very well studied, and the importance of, because most of the country like Australia are actually covered by thick regolith layers, and this is similar the situation in many parts of our country, where the study of regolith have been very important over the recent past 1 or 2 decades. And if we could see here one of the regolith profile. So, the regolith is broadly divided into a saprolith and pedolith. Pedolith essentially is the soil part of it, and the saprolith is actually the altered rock part of it. And like the soil profile, we see at the base of it is the rock, which is the unweathered part of the rock, and just above the rock in the saprolith layer, in the saprolith zone, we get the sap rock, which is essentially containing the fragment of the bedrock and will be 20% about weatherable minerals is altered, followed by the saprolite, which will be a layer where its primary fabric pseudomorph, but recognizable of the parent rock, and this is a kind of you can call it as pedoplasmation front, means formation of the, this is the front which actually goes over to formation of the fresh soils, and there is the clay zone, which is the primary fabric replaced by clay or quartz rich secondary structures, and then it come to cementation front, and the top is essentially the soil, followed by a dewey crust, means a compacted layer which consists of the ferruginous material, iron oxide material, and that is how it is shown by the piezolytic kind of structure. And in the pedolith, it is basically divided by a plasmic or the arenose zone, the mottle zone, the dewey crust, and the soil. So, this soil is on it is shown on a cross section here, and so this profile, this regolith profile needs to be studied well, and in areas, if there is a plan of carrying out a geochemical prospecting, then the regolith profile is something which is very has to be understood very properly. And here this it can be seen on a section that these layers, which are this the erosional regime, in which the lowest part of the this plasmic arenose zone is exposed, and on the top part we could see the saprolitic bedrock, and this is colluvium, and so they have different reflections, and this soil and the regolith geochemistry is then now being very actively studied for as a tool for mineral exploration in many different parts of the world, including the one which I have said. So, this is taken from Anand and Bhatt in 2010. The different layers which are shown here, the ferruginous dewey crust, which is the top layer, which is above here, and it's been dissected by the normal erosion process, and then the sap rock part is exposed with the wattle by the this is the deepest part, which is the soil, the fresh rock identified aeolian material is so sometimes they could be also of aeolian origin, where the aeolian contribution has to be identified, and this is very critical. And so here the bedrock, the saprolite, it was shown before, the iron saprolite, the ferruginous debris crust, colluvium, and the recent alluvium, which is this part is the forming the recent alluvium here just along the river channels. So, this also requires a very detailed study as to during the geochemical prospecting program, which part of the regolith or where the regolith, how the regolith has to be sampled, so that it could give us meaningful indications, results, and analysis for our interpretation for geochemical anomalies. So, what exactly is preceded before a analytical work or before exactly a soil sample is taken? So, essentially it is known as an orientation survey, the pilot investigation. So, to establish the optimum routine field analytical and interpretative procedure. So, it actually is preceded by something which is a orientation survey. So, this orientation survey, before we take up any particular sample for analysis, so there should be clear understanding of the target, that is type. So, knowledge of subsurfacial environment, the sample types available, the sample collection procedure, means when we are talking about the soil profile, normal soil in any particular geographical region, there we must know that how deep we should collect the sample, so that we represent the exact zone which will be reflective of exactly subsurface condition. The sample interval, orientation and density. The sample interval is a very important decision to be taken, because it depends on the dimension of the targeted ore body, and in case the for example, if there is a situation depending on how the ore So, suppose there is an area where, and we expect that there should be an ore body somewhere here, somewhere it is just the surface outcrop which I am just representing, and if I plan the sampling interval, that sampling that I am taking for the soil, and depending on the grid that I am following for the sampling, how closely spaced or how widely spaced the sampling, if this is the grid on which we are taking the sample, presuming that we are taking on a regular interval, and it might so happen that depending on the outcrop, depending on the size and shape or orientation of the particular hidden ore body, we might even miss the signature of the ore body if the sampling interval is not exactly proper. So, there are many exploration programs which fail because of improper anywhere, any of the deficiency, where if the sampling density, sampling pattern is somewhat not appropriate, then the field observations required, sample size requirements, and the which fraction of the sample to be analyzed, so that that fraction will actually be reflecting, or that fraction will only be, because the metals of interest may not always be present in all the fractions of the soil, which is a mixture of all different size fractions. Sometimes it may be the very small fractions less than 2 millimeter, even the clay or the soil, the shape, clay particles, there the metal of interest may be more because of adsorption, and the coarser particle may not have the metals, and then depend that decision has to be made initially very firmly, that which fraction has to be analyzed. then the analytical method that is going to be selected, and the geochemical suit and the data format, and then these types of orientation survey will be based on the public data that is reviewed, on the case histories and experts opinion consultants. These are some of the examples here. So, this is a schematic section of a ore body which is there below a shale, and this has been cut by. So, this is the layer which is mineralized, and it is cut by fault, and this if there are sampling which is done on this particular surface, and then we might get some kind of anomaly here. So, these are the structural control geochemical anomaly. This cross section shows use of the surface rock chip sampling to detect leakage anomalies. So, these are the anomalies, the elements will definitely have a higher mobility on this kind of faults and fractures, and the anomalies will become clearer. And this is also an example how if there is a hidden ore body somewhere here, it is shown by the lead enriching ore body bedrock, and it has been dissected by the streams. So, the stream channels will have the if we analyze the stream channel, for example, so the weathering of the lead enriching ore body is producing the anomalous dispersion train. So, here we will be essentially be sampling the train which is found by the by this river, and we can trace back all the, because for example, if we look into the sediments of this particular order streams, we will not get anything, and only we will be getting in this, and that is how it will make us target or reach at the target that we are looking for. So, these are some of the patterns that form. So, this gives an idea about the pattern, the results of soil sampling in an area of stream sediment. So, this is how the stream sediments are analyzed, and the grid is made for the soil survey. These are the contours, and after we do the analysis, the analytical result can be represented in the form of a geochemical anomaly map, and joining the points of equal values to form such kind of contours. And this you could see is very clearly here that if the ore body which is lying in this particular region, then the contour values are increasing 200, 500, 1000 and 2000, and that is how instead of so there are several such profiles which are compiled together. And okay, so we will continue our discussion on the geochemical methods of prospecting. Thank you.